In the previous demo, we computed the temperature and salinity climatology for the North Pacific grid, which was our example. We are now going to use these TS to compute the geostrophic flow. So we're going to go in the NC files directory again. This time we're going to work with the file called main NC files clima_UV, which is the one that computes the climatology, that computes the geostrophic flow from the climatology. In a different shell here, I'm going to go again in NC files and fire MATLAB. Okay, so the first thing that this script does, it basically selects what grid you're working with, and it only does this if you haven't defined the name it yet. But if you don't, in this case I don't, because I just started MATLAB, so I'm just going to execute this, and so I'm working with this grid here. Okay, so the first thing that I do here is I assign this variable do geostrophic from clima file equal to 1. And that's because it enables the block that actually does the geostrophic calculation. The fact that you have this switch is because this particular script can be used, can be called within a big script that does all the processing for you. And in this case, you could use this as a switch to enable or disable the geostrophic flow calculations. For example, if you were to use the SODA dataset, you may not want to compute the geostrophic flow, so you could just turn this off. So the first thing that we do when we compute geostrophic flow, we realize that this is not a rigorous calculation. And that's obvious because geostrophic flows, unless you have a real reference velocity from which to integrate, it is all like reference to some assumption of level of no motion. But let's get started. So the first thing we do is we load the climatological file, and keep in mind that this doesn't necessarily have to be a climatological file of TS. It can be any kind of file that has, TS data on the ROMS grid that you want to compute the geostrophic flow. Then I assign a reference density, so I'm just going to compute that. Okay. Then where we have a loop here, that for each time record contained in this climatology file, it's going to basically do this geostrophic calculation. So let's try one of the records. Let's say IT equals 1. And so what do we do next? Well, the first step is to load the temperature and salinity associated with that record. So we do that here. Okay. The next thing is we execute this function here called rnt_calc_ssh. And what this function does, it basically computes the U and V geostrophic flow and the dynamic height and stores that in SSH. So it's called rnt_calc_ssh. It wants as input the temperature, the salinity, the grid. Then it wants to know where you want to reference the geostrophic flow. What is the level of no motion? And in this case, I like to use the bottom. You can use other level of no motions. Another commonly used value is 500 meters. But in my experience, I noticed 500 meters is not a very good level of no motion, because a lot of the eddy structures, especially in the coastal regions and also in the deeper ocean, extend way beyond 500 meters. Then there's this other input parameter that is also in meters, and this is set to 500, and this is the level, reference level that will be used to compute or to estimate the dynamic height, of the model, relative to this temperature and salinity. You may want to use the same. For example, you would say, why don't you use bottom in both? If you use the bottom for the dynamic height calculation, it's not very good, and so I decided to use 500 meters. This is just an estimate of all these things. These are not very accurate. So let's execute that, and if we execute this, it usually doesn't take very long. In fact, it's done. And at this point, we can make, for example, a figure PLCM of the dynamic height calculation. This again, it's for North Pacific grid, and what we find is that indeed this is consistent with the large-scale mean circulation. We find here this Kuroshio-Washo region current, the North Pacific current. This goes down the way here, the California current coming down, and the Gulf of Alaska circulation, or the subpolar gyre, going all around. So this is pretty much consistent with the subtropical cell and the subtropical gyre and subpolar gyre. So this is pretty good, and these ranges have been the mean has been taken out so that you could use this as an initial input for your ROMS model. We can also look at a vertical section of the geostrophic flow. In this case, let's plot a vertical section along the meridional direction, along here, and RNT sect Y. And we're going to plot the zonal flow, and we're going to use the index I equals 60 and GRD. Okay. And so this is what you get. So around 40, you find that there's a very positive area of zonal flow. And if we go along 40 here, okay, you find that in fact you're in the middle of the North Pacific Current, and this flow is in fact going in the positive direction towards the east. So it's consistent with this, okay? And you have some subsurface flow close to the equator that is going in the opposite direction, and this represents more or less the closure, you know, of this subtropical gyre. So this is all very consistent. Now, of course, here I use the bottom as a reference velocity. You could decide to use a different reference velocity. As I said, suppose that you say you put a level of no motion at 500 meters. You can redo this calculation. And we can plot again a vertical section of the velocity. Okay, and now you see that in the vertical section you still have the North Pacific Current here around 40 degrees north, but now you see that you have this zero level of no motion right at 500 meters, and so the velocity changes sign and so forth. And to my experience, if I compare this geostrophic calculation with this, it seems to me that this level of no motion of the bottom is a little bit better as an initial start. Okay, so this now you have now a way to estimate the geostrophic flow. And really all the reason why you're doing that is mostly because some of this may be useful when you use the climatology as the initial condition to start the model with something, or you know, if you need to provide some open boundary conditions. Now once we do that, there's other things we can do. For example, sometimes it may be worth to add at the surface an Ekman velocity, a geostrophic velocity, which is computed from the winds. And so in this case you would load the forcing file. You will load tau x and tau y, which are the wind stresses, and then you would use this function to compute the Ekman currents. And of course computing the Ekman currents is not so trivial, because you need to make some assumptions about, you know, the vertical viscosity in the Ekman layer and so forth. So this calculation is really not accurate at all, and I have not been very satisfied with it. So I typically don't really run the Ekman. I don't add the Ekman currents, so I just leave them out. The next thing though is we have U, V, and SSH, but we also have to compute the vertically integrated flow, and so here is a function to compute U bar and V bar, which is called RNT barotropic, and it wants this UGO, VGO, HZ out, which is the thickness of the sigma layer, and then the grid. After I compute this, then all you need to do is you need to save these U's, V's, and Zetas, and U bar and V bar into the climatology file, and then you're done. So with this in mind, then this script here can be just executed from MATLAB directly if you want, and we're just going to do it. And at this point, you know, it's going to just compute all the geostrophic flows. It's doing it, and then for each time is going to save the various variable U, V, zeta, U bar, V bar in the appropriate time record. And so now it's just doing, you know, month number 3, which in this case would be March, and now what is it, April, and so forth. So this concludes the section on computing geostrophic flow. Keep in mind that if you want, you can use this geostrophic calculation. Actually, I want to say few more words about this. This geostrophic calculation, actually, if you had this function, inside this function, we have actually. I want to stop this 1 second. If I do which F12, you actually can compute, if you, for example, have an output of the model and you want to compute the geostrophic flow and you have the actual sea surface height from the model, then you can actually compute the absolute geostrophic flow using the pressure gradient routine of the model, which this function uses, in fact. And so for example, if we go in this function, there's a place here where you do the actual UGO calculation right here, okay? and there's a function that is available in your RNT toolbox called RNT-PRS-V2. And this, if you have the right sea surface height, suppose you have a model integration and you want to compute just the geostrophic component of the flow, you can actually use this function to accurately recompute the geostrophic flow using the same numerics of the model. So that's very useful, because by doing that, really, then you can compute the geostrophic flow and you can subtract that by from the absolute velocity that the model estimated, and what's left over is the ageostrophic component of the flow, which it would be, for example, the Ekman layer. So this is a very useful routine to keep in mind, this RNT PRS V2, and you can try this on a model output to have fun. The inputs are all things that the mask, the density, a reference density, ZR, ZW, HZ, these are all things you have. Okay, so that's kind of a useful thing to keep in mind of how to compute geostrophic flow. And I'm not going to provide an example because otherwise this tutorial is going to get too long. But what I'm going to do is I'm going to copy this and I'm going to store it here in this. If we go here in the edit, I'm going to put a note here so that you have it. I'm going to put a comment here. If you had the exact zeta from a model run, you can compute the total, the absolute geostrophic flow using the pressure gradient routine of ROMs contained in the function RNT-PRSV2. Okay, so this is just so that you have it in case you want to try it out. Okay, so this concludes our tutorial on the geostrophic flow.